Tonight, we're going to explore a distance so vast that it literally breaks the human mind. A light year. Most people think they understand it. A unit of distance, something astronomers use because space is big. But that's not the whole story. When you actually understand what a light year means, when you sit down and work through what this distance really represents, something happens. The numbers stop being just numbers. They become distances so incomprehensibly large that your brain hits a wall. It was never designed to climb over. Scientists use light years because nothing else works at cosmic scales. Miles and kilometers become meaningless when you're measuring the space between stars. But that's not all. A light year isn't just a really big distance. It's a measure that fundamentally connects space and time. And when you understand that connection, everything changes. Every star you see in the night sky is already history. Not metaphorically, but literally. When you look up at the stars, you're not seeing them as they are right now. You're seeing them as they were years ago, decades ago, centuries ago, sometimes millions of years ago. You're looking directly into the past. By the end of tonight, you're going to understand exactly how far a light year is, why even the closest stars are unreachably distant, and why this one unit of measurement reveals just how isolated we really are in the cosmos. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something familiar. Distance. You know what a mile means, what 5 miles feels like, what 200 miles requires. These are human-scaled distances, the kind our brains evolved to understand. But those measurements completely fall apart when we leave Earth. The distance from New York to Los Angeles is about 2,800 miles. That's a big number, but it's still something we can work with. It's about a 5-hour flight. People make that journey all the time. You can imagine crossing the continent, seeing the landscape change from East Coast cities to Midwest plains, to Rocky Mountains to Southwest deserts, and finally to the Pacific coast. The journey is long, but it's achievable. It's within human capability. You can imagine making that trip. The Earth's circumference at the equator is about 24,900 miles. That's a bigger number, but it's still something we can conceptualize. Early explorers sailed around the world, so we know it's possible to travel that distance even if it takes months. We have a sense, however vague, of what circumnavigating the globe means. But now, we're going to start pushing beyond these human-scaled distances. We're going to start moving into territory where our intuition begins to fail us. The distance from Earth to the Moon is about 238,900 miles. Now we're getting into numbers that are harder to grasp. Nobody has walked to the Moon. Very few people have even been to the Moon. And when they went, it took them about 3 days in a spacecraft traveling at tremendous speed. You can't visualize what 238,900 miles looks like. It's too big. It doesn't connect to anything in your daily experience. You can calculate with it, you can write it down, but grasping it intuitively is nearly impossible. The Apollo astronauts who went to the Moon described looking back at Earth and seeing it as a small blue marble against the blackness of space. That's how far away they were. Far enough that the entire Earth, all 7 continents, all the oceans, all the billions of people, everything fit into a view small enough to cover with your thumb at arm's length. And they were only at the Moon. The distance from Earth to the Sun is about 93 million miles. We call this distance 1 astronomical unit, and it's a fundamental measurement in astronomy because it's the baseline we use to measure distances to everything else in the solar system. Mars is about 1.5 astronomical units from the Sun. Jupiter is about 5 astronomical units. Neptune is about 30 astronomical units. But even one astronomical unit, the distance from Earth to the Sun, is almost incomprehensible. 93 million miles. Try to visualize that. You can't, can you? Your brain just sees it as a really big number, but you don't have any intuitive sense of what it actually means. There's nothing in your daily life that prepares you for a distance like that. Nothing in human evolution prepared us to think about distances this large. We evolved to understand the distance to the next water source, the distance to the hunting grounds, the distance we could walk in a day. We didn't evolve to comprehend 93 million miles. The Apollo spacecraft that took astronauts to the moon traveled at about 6,800 miles per hour on average. At that speed, it would take about 570 days, over a year and a half, to reach the Sun's distance. The fastest spacecraft humans have ever built, the Parker Solar Probe, travels at speeds up to 119,000 miles per hour. When it's close to the Sun, using the Sun's gravity to slingshot itself to higher and higher speeds. Even at this incredible speed, which is about 17.5 times faster than the Apollo spacecraft, the probe still takes months to complete its orbits around the Sunday, and the Sun is close. It's right here in our cosmic neighborhood. It's the star we orbit. It's the source of all the light and heat that makes life on Earth possible. We see it every day. It's familiar. And yet, it's 93 million miles away, a distance so vast that even our fastest spacecraft takes months to traverse it. When we start talking about distances to other stars, even the Sun's distance becomes tiny by comparison. The Sun is our nearest star, and it's 93 million miles away. The next nearest star, Proxima Centauri, is about 266,000 times farther than that. 266,000 times farther than a distance that already takes our fastest spacecraft months to cover. This is where traditional units of measurement completely break down. This is why astronomers needed something different. Not because they like making things complicated, not because they want to confuse people with big numbers, but because miles simply don't work when you're measuring cosmic distances. Using miles to measure distances to stars would be like using inches to measure the distance between countries. Technically possible, but completely impractical. The numbers become so large they lose all meaning. They stop being distances and become just numbers, abstract mathematical concepts that don't connect to anything in our experience. So astronomers came up with something different, the light year. But here's what you need to understand right from the start, and this trips up almost everyone when they first encounter the term. A light year is not a measure of time. I know it has the word year in it, which makes it sound like time, but it's not. A light year is a measure of distance. It's the distance that light travels in 1 year. Now, why base a measurement on light? Because light is special. Light is the fastest thing in the universe. Nothing can travel faster than light. This isn't just a speed limit that we haven't broken yet. It's a fundamental law of physics, a property of the universe itself, built into the very fabric of space-time. The speed of light is a constant, unchanging, the same everywhere in the universe. Whether you're on Earth, on Mars, in another galaxy, or at the edge of the observable universe, light always travels at the same speed. Light travels at about 186,282 miles per second. Let me say that again because it's important. 186,282 miles per second. Every single second, light travels 186,282 miles. That's incredibly fast. To put it in perspective, light can travel around the Earth's equator about 7.5 times in 1 second. In the time it takes you to snap your fingers, light could circle the entire planet multiple times. In 1 second, light could travel from New York to Los Angeles and back about 37 times. It's a speed that's almost impossible to visualize, because nothing in our everyday experience moves anywhere near that fast. The fastest thing most people experience is an airplane. A commercial jet flies at about 550 miles per hour. Light travels over 600,000 times faster than that. The fastest car ever built, the Thrust SSC, reached about 763 miles per hour. Light is about 243,000 times faster. Even the fastest spacecraft we've built, the Parker Solar Probe at 119,000 miles per hour at its peak, is still only about 0.064% the speed of light. It's moving incredibly fast by human standards, but compared to light, it's crawling. When you turn on a light switch, the light reaches your eyes essentially instantly because the room is so small. The light travels from the bulb to your eye in about 10 billionths of a second. That's so fast that there's no perceptible delay. As far as your brain is concerned, the light appears instantly, but the light did travel. It took time. It's just that the time was so short you couldn't possibly notice it. When you see the sun in the sky, you're actually seeing it as it was 8 minutes and 20 seconds ago, because that's how long it takes light to travel from the sun to Earth. The sun is so far away, 93 million miles, that even light traveling at 186,282 miles per second needs over 8 minutes to cover the distance. Think about what that means. When you look at the sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes and 20 seconds ago. If the sun suddenly vanished right now, winked out of existence, we wouldn't know for 8 minutes and 20 seconds. For those 8 minutes and 20 seconds, the sun would still appear to be shining in the sky, Earth would still be receiving light and heat, nothing would seem wrong, because the last light the sun emitted before vanishing would still be traveling through space toward us. Only after those 8 minutes and 20 seconds would the sky suddenly go dark and the temperature start to drop. This is one of the strange consequences of the finite speed of light. We're always looking into the past. When we look at anything in space, the farther away something is, the farther back in time we're seeing it. This connection between distance and time is fundamental to understanding what a light year means. When astronomers say a star is 10 light years away, they're telling you two things simultaneously. First, they're telling you how far away it is, the distance light travels in 10 years. Second, they're telling you that when you look at that star, you're seeing light that left the star 10 years ago, you're seeing the star as it was 10 years in the past. If that star exploded today, we wouldn't see the explosion for 10 years. For the next 10 years, that star would continue to appear in the sky, looking perfectly normal because the light from the explosion hasn't reached us yet. So a light year is the distance light travels in 1 year at this incredible speed. Let's calculate exactly what that means. Light travels at 186,282 miles per second. There are 60 seconds in a minute. There are 60 minutes in an hour. There are 24 hours in a day. There are 365 days in a year. If we multiply all of these together, 186,282 times 60 times 60 times 24 times 365, we get approximately 5,878,625 miles. To be more precise, it's 5,878,625,373,183.6 miles. But for simplicity, we usually just say 5.88 trillion miles. That's what a light year is. 5.88 trillion miles. Not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in 1 year. And that's the number we're going to try to understand tonight. Because understanding what a light year means is essential to understanding our place in the universe. the distances between stars, the true scale of the cosmos. But first, we need to talk about what a trillion actually means, because most people have no intuitive sense of how large this number really is. We throw around words like million, billion, and trillion in everyday conversation. We hear about government budgets in the trillions, about billionaires, about millions of people, but we don't really understand the massive differences between these numbers. They all sound like big numbers, so we treat them as roughly equivalent. But they're not. The differences between them are staggering. A million is 1,000 thousands. If you started counting right now, out loud, one number per second, and you counted continuously without sleeping, without eating, without taking any breaks whatsoever, it would take you about 11.5 days to count to a million. That's conceivable. You can imagine counting for 11.5 days straight. It would be exhausting and miserable, but it's within the realm of human possibility. A billion is 1,000 millions. Now we're jumping up by a factor of 1,000. If you counted one number per second, you'd need about 32 years to count to a billion. That's more than the time it takes for a generation to grow up. If you started counting when you were born and counted continuously without sleeping, eating, or taking any breaks whatsoever, you'd be 32 years old when you reached a billion. Think about that. A million seconds is about 11.5 days. A billion seconds is about 32 years. The difference between a million and a billion is enormous. A trillion is 1,000 billions. We're jumping up by another factor of 1,000. If you counted one number per second, you'd need about 32,000 years to count to a trillion. That's longer than all of recorded human history. When humans first started farming, when we built the first cities, when we invented writing, we still wouldn't be done counting. By the time ancient Egypt rose and fell, by the time the Roman Empire rose and fell, by the time the Renaissance happened, by the time the Industrial Revolution transformed society, we'd still be counting. A trillion seconds ago, humans were still living in small hunter-gatherer tribes, making stone tools, with no agriculture, no writing, no civilization, nothing we would recognize as modern human society. That's how far back a trillion seconds takes you. And a light year is 5.88 trillion miles. Every single one of those miles is a mile, a real distance, the distance you could walk in about 15 to 20 minutes at a normal pace. And there are 5.88 trillion of those individual miles in one light year. 5.88 trillion separate, distinct, mile-long segments, each one the length of a walk to your local store. So when we say a light year is 5.88 trillion miles, we're talking about a distance that absolutely dwarfs anything in our daily experience. You can write it down, you can calculate with it, you can use it in equations, but grasping it intuitively is nearly impossible. Our brains simply didn't evolve to handle numbers this large. We evolved to count the number of people in our tribe, the number of animals in a herd, the number of days until the seasons change. We can count to a few hundred, maybe a few thousand if we really concentrate, but 5.88 trillion is so far beyond our cognitive capabilities that it might as well be infinity. The best way to understand a light year is to build up to it gradually, starting with distances we can comprehend and scaling up step by step. We're going to take this journey slowly, moving from the familiar to the unfamiliar, watching as distances that seem vast become tiny compared to what comes next. Let's start with 1 light second. 1 light second is the distance light travels in 1 second, which is 186,282 miles. That's about 3/4 of the distance from Earth to the Moon. Think about what that means. Light leaves Earth, travels almost all the way to the Moon, and all of that happens in 1 second. 1 single second. When astronauts on the moon talked to Mission Control in Houston during the Apollo missions, there was a communication delay of about 1.3 seconds each way. The astronauts would say something and Mission Control wouldn't hear it for 1.3 seconds because the radio signal, traveling at the speed of light, needed that long to make the journey. When Mission Control replied, their response took another 1.3 seconds to reach the moon. So, every exchange had a nearly 3-second delay built in. It's subtle when you listen to the recordings, but it's always there, this pause, this lag, because of the distance the signals had to travel, and because nothing, not even radio waves, can travel faster than light. 1 light minute is 60 light seconds, which is about 11,169,600 miles. The Sun is about 8 light minutes away from Earth, which is that 93 million miles we talked about earlier. So 1 light minute is roughly 12% of the distance from Earth to the Sunday. Mars, depending on where it is in its orbit, is between about 4 and 20 light minutes from Earth. This means that when we send commands to rovers on Mars, there's a significant communication delay. If Mars is at its closest approach to Earth, a signal from Earth to Mars takes about 4 minutes, and the response takes another 4 minutes to come back. So any communication has an 8-minute round-trip delay built in. When Mars is on the opposite side of the Sun from Earth, that delay can be over 40 minutes round-trip. This is why Mars rovers have to be partially autonomous. They can't be controlled in real time like a remote control car. The delays are too long. If a rover is about to drive off a cliff, it needs to detect that and stop itself, because by the time a warning signal from Earth arrives, it would already be too late. 1 light hour is 60 light minutes, which is about 670 million miles. Jupiter is about 43 light minutes from the Sun. Saturn is about 80 light minutes, which is about 1.3 light hours. These are the outer planets of our solar system, and they're so far away that light from the Sun takes over an hour to reach them. If you were standing on Saturn, watching the Sun rise, you'd be seeing the Sun as it was over an hour ago. 1 light day is 24 light hours, which is about 16 billion miles. This takes us beyond the orbits of all the planets. Neptune, the farthest planet from the Sun, orbits at about 2.8 billion miles from the Sun, which is only about 4 light hours. Beyond Neptune, there's the Kuiper Belt, a region of icy bodies including Pluto, and beyond that, there's the scattered disk, and eventually the Oort cloud, a vast spherical shell of comets that extends perhaps as far as 1 light year from the Sunday. But we're not there yet. We're still building up. 1 light week is 7 light days, which is about 112 billion miles. 1 light month is about 30 light days, which is about 480 billion miles. We're now well beyond the planets, out in the region where comets occasionally fall inward toward the Sun, their icy surfaces vaporizing as they get closer to the Sun's warmth. 1 light year is 12 light months, which is 5.88 trillion miles. We started with distances we understand. A mile, something you can walk in 15 to 20 minutes. We've been multiplying by larger and larger numbers. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 7 days in a week, 30 days in a month, 12 months in a year. And we're just now getting to 1 light year. 5.88 trillion miles. That's the distance light travels in 1 year, moving at 186,282 miles every single second for 365 days straight. And this is the fundamental unit astronomers use to measure distances between stars, because stars are separated by distances measured in light years, and nothing smaller makes sense when you're dealing with these vast cosmic scales. So why do astronomers use light years? Because every other option is worse. Imagine if astronomers used miles for everything. Proxima Centauri is about 24,900,000,000,000 miles away. That's awkward, hard to remember, and doesn't give you any intuitive sense of the distance. But if I tell you Proxima Centauri is 4.24 light-years away, that's cleaner, easier to remember, and you can compare it to other distances. If one star is 4 light-years away and another is 40 light-years away, you immediately know the second is 10 times farther. Light-years also connect distance and time in a useful way. When you look at a star 4 light-years away, you're seeing light that left 4 years ago. You're looking into the past. This connection becomes crucial when studying the universe. The farther away something is, the farther back in time we're seeing it. Distant galaxies we observe through telescopes are seen as they were billions of years ago, when the universe was young. The speed of light is not just fast, it's the speed limit of the universe. Nothing can go faster. And this isn't a technological limitation that we might overcome with better engineering or more powerful rockets. It's a fundamental law of physics, built into the very structure of space-time itself. The speed of light isn't just a speed, it's a cosmic constant that defines the relationship between space, time, energy, and matter. Einstein's theory of special relativity, published in 1905, showed that as objects approach the speed of light, strange things happen. And these aren't just theoretical predictions, they're observed facts, confirmed by countless experiments over the past century. Time slows down for the moving object relative to stationary observers. This is called time dilation, and it's been measured directly. The object's mass effectively increases, or more precisely, its inertia increases. It becomes harder and harder to accelerate. The amount of energy required to accelerate it increases without limit as you approach light speed. To actually reach the speed of light would require infinite energy, which is impossible. The universe doesn't contain infinite energy. Therefore, nothing with mass can reach the speed of light. Let me explain why this happens. In our everyday experience, if you're on a train moving at 50 miles per hour and you throw a ball forward at 20 miles per hour relative to the train, someone standing on the ground would see the ball moving at 70 miles per hour. The speeds add. This seems obvious, and it works perfectly well for everyday speeds. But Einstein showed that this simple addition breaks down as you approach the speed of light. If you're on a spaceship moving at 90% the speed of light and you shine a flashlight forward, you might think the light from the flashlight would be moving at 190% the speed of light, the ship's speed plus the light's speed. But it doesn't work that way. Someone watching from a stationary position would still see the light from your flashlight, moving at exactly the speed of light, not faster. How is this possible? Einstein realized that space and time must be flexible. They adjust themselves to ensure that the speed of light remains constant for all observers, regardless of how fast they're moving. If you're moving fast enough, time actually slows down for you relative to stationary observers, and space contracts in the direction you're moving. These effects ensure that you and the stationary observer both measure light moving at the same speed, even though you're moving relative to each other. This has been tested experimentally many times. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground. Particles in accelerators moving at 99.9% the speed of light live much longer than they do when at rest, because time is running slower for them. GPS satellites have to account for relativistic time dilation, both from their orbital speed and from being higher in Earth's gravitational field. Otherwise, GPS navigation would become inaccurate within minutes. The point is, the speed of light is absolute. It's baked into the laws of physics. Nothing with mass can reach it, much less exceed it. This means that distances measured in light years represent real barriers to communication and travel. Stars that are light years away are separated from us not just by space, but by time. Even traveling at the speed of light, which is impossible for anything with mass, you'd still need years to reach nearby stars, and millions of years to reach distant galaxies. Before we dive into actual distances to stars, we need to understand just how difficult it was for humanity to even begin measuring these distances. For thousands of years, humans looked up at the stars and had absolutely no idea how far away they were. Ancient Greek astronomers thought the stars might be holes in a celestial sphere, or perhaps they were lights attached to crystal spheres that rotated around Earth. The idea that stars were actually distant suns, so far away that their light took years to reach us, would have seemed absurd. It wasn't until the 17th century that astronomers even had the tools to begin attempting to measure stellar distances. The basic principle is called parallax, and it's something you can demonstrate with your own eyes right now. Hold your finger up at arm's length and look at it with just your left eye closed. Now switch. Close your left eye and open your right. Your finger appears to shift position against the background, doesn't it? That's parallax, the apparent shift in position of a nearby object when viewed from two different locations. The farther away an object is, the smaller the parallax shift. Your finger has a large shift because it's close. A tree across the street would have a smaller shift. A mountain on the horizon would have an even smaller shift, and something infinitely far away would have no shift at all. Astronomers realized they could use this principle to measure distances to stars. Earth orbits the Sun, which means Earth's position in space changes throughout the year. In January, Earth is on one side of the Sun. In July, Earth is on the opposite side of the Sun, about 186 million miles away from where it was in January. If you observe a star in January, note its position carefully against the background of more distant stars, then observe the same star in July from the opposite side of Earth's orbit. You should see it shift slightly. The amount of shift tells you how far away the star is. The smaller the shift, the farther the star. Simple geometry, basic trigonometry. The problem was that the shifts were incredibly tiny, far smaller than anyone expected. The best telescopes of the 17th and 18th centuries could barely measure angles of 1 arcsecond. An arcsecond is 1/60th of an arc-minute, which is 1/60th of a degree, so 1 arcsecond is 1/3600th of a degree. To give you a sense of how small that is, if you hold a dime at a distance of about 1.5 miles and look at it, the dime appears about 1 arcsecond across. That's the level of precision required. And even that wasn't enough, because the nearest stars have parallax shifts smaller than 1 arcsecond. Robert Hooke tried in 1669 and failed. James Bradley tried in the early 1700s and failed, though he discovered stellar aberration, a different effect caused by Earth's motion through space. William Herschel, the astronomer who discovered Uranus, tried for years and failed. It wasn't until 1838 that Friedrich Wilhelm Bessel finally succeeded. Bessel was a German astronomer and mathematician, one of the most careful and precise observers of his time. He had improved methods for correcting telescope observations for atmospheric refraction, for Earth's motion, for all the various sources of error that plagued astronomical measurements. He chose his target carefully, a star called 61 Cygni in the constellation Cygnus. 61 Cygni wasn't chosen because it was bright. It's actually quite faint. You need a telescope to see it at all. But Bessel noticed that 61 Cygni had a large proper motion, meaning it was moving across the sky relative to other stars over time. This suggested it was relatively close. Stars that are very far away appear to move very slowly across the sky over time because they're so distant that even their actual motion through space produces only tiny, apparent motion from our perspective. Stars that are close appear to move faster, so Bessel focused on 61 Cygni, made careful measurements over more than a year, accounting for every source of error he could think of, and finally, in 1838, he announced his result. 61 Cygni had a parallax of about 0.314 arcseconds. Using this measurement and basic trigonometry, Bessel calculated that 61 Cygni was about 10.3 light-years away. Modern measurements, using much better instruments, confirm Bessel was right. 61 Cygni is about 11.4 light-years away. Bessel's measurement was accurate to within about 10%. This was a monumental achievement, one of the great triumphs of 19th-century astronomy. For the first time in human history, we had an actual measured distance to a star. We knew how far away they were. We knew the stars were not attached to a celestial sphere just beyond the planets. They were unimaginably distant objects, so far away that their light took years to reach us. Almost simultaneously, two other astronomers made similar measurements. Thomas Henderson, a Scottish astronomer, measured the parallax of Alpha Centauri, one of the brightest stars in the southern hemisphere sky. Friedrich von Struve, a German astronomer working in Russia, measured the parallax of Vega, one of the brightest stars in the northern hemisphere. All three measurements were published in 1838 and 1839. All three confirmed the same stunning fact: the stars were light-years away. The nearest stars had parallaxes of less than 1 arcsecond, which meant they were several light-years distant. Fainter stars, which presumably were either more distant or intrinsically dimmer or both, were even farther. The Milky Way, that band of light stretching across the night sky, wasn't a nearby cloud or atmospheric phenomenon. It was composed of countless stars, each one light-years away. The scale of the universe suddenly became clear, and it was vastly larger than anyone had imagined. This was one of the great paradigm shifts in human history, comparable to Copernicus showing that Earth orbits the Sun, or Darwin showing that life evolved through natural selection. The universe was not human-scaled. It was not designed with humanity in mind. It was vast, almost beyond comprehension, and humanity occupied a tiny corner of it. The measurement of stellar parallax opened up a new era in astronomy. Now astronomers could measure distances directly, at least to nearby stars. They could determine the true brightness of stars by comparing their apparent brightness to their distance. They could start to understand the physical properties of stars, their temperatures, their sizes, their masses. They could begin to map the structure of our galaxy and eventually realize that our galaxy was just one of billions. All of this stemmed from measuring tiny angles, fractions of an arcsecond, and using those measurements to calculate distances in light-years. Let's talk about some actual distances to real objects in space to make this more concrete. Proxima Centauri, the closest star to our Sun, is 4.24 light-years away. That's 24,900,000,000,000 miles. If you could somehow travel at the speed of the Parker Solar Probe, our fastest spacecraft at 119,000 miles per hour, it would take you about 23,900 years to reach Proxima Centauri. That's longer than all of recorded human history. When the first cities were being built in ancient Mesopotamia, when writing was first invented, if a spacecraft had launched then traveling at the Parker Solar Probe's speed, it still wouldn't have reached Proxima Centauri yet. It would only be about halfway there, and Proxima Centauri is our nearest neighbor. The next nearest stars after Proxima Centauri are part of the Alpha Centauri system, and they're also about 4.37 light-years away. Barnard's star is about 6 light-years away. Sirius, the brightest star in our night sky, is 8.6 light-years away. Every star you can see with your naked eye in the night sky is within about 1,000 light-years of Earth. Most are much closer, within a few hundred light-years. The stars that make up the constellations, The patterns we see in the sky are at various distances. Some might be 40 light-years away, others 400 light-years away, but they appear to be next to each other in the sky because they happen to lie along the same line of sight from Earth. Betelgeuse, the red supergiant star in the constellation Orion, is about 550 light-years away. When you look at Betelgeuse in the night sky, you're seeing light that left that star 550 years ago. You're seeing Betelgeuse as it was during the Renaissance, around the time Columbus sailed to the Americas. If Betelgeuse exploded today, we wouldn't see it for 550 years. For the next 550 years, Betelgeuse would continue to appear as a bright red star in Orion because the light from the explosion hasn't reached us yet. The center of our Milky Way galaxy is about 26,000 light-years away. When you look toward the galactic center, you're seeing light that left 26,000 years ago, when humans were still hunter-gatherers, when mammoths and saber-toothed cats still roamed the Earth. Our entire galaxy, the Milky Way, is roughly 100,000 light-years across from one edge to the other. To cross our own galaxy at the speed of light, you'd need 100,000 years. That's longer than modern humans have existed as a species. Homo sapiens evolved about 300,000 years ago, but behavioral modernity, the development of language, art, complex tools, that's only about 100,000 years old. So to cross the Milky Way at the speed of light would take about as long as behaviorally modern humans have existed. The Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years away. When you look at Andromeda, you're seeing light that left that galaxy 2.5 million years ago, long before humans evolved, when our ancestors were still small ape-like creatures in Africa. The Andromeda Galaxy is so far away that its light has been traveling toward us for millions of years, crossing vast empty reaches of intergalactic space, and it's only just now reaching our eyes. The local group, the cluster of galaxies that includes the Milky Way and Andromeda, spans about 10 million light-years. Beyond the local group, there are other galaxy clusters. The Virgo cluster, one of the nearest large clusters, is about 50 million to 60 million light-years away. The observable universe, the portion of the universe we can see, extends about 46.5 billion light-years in every direction from Earth. Wait, you might be thinking, how can the observable universe be 46.5 billion light-years across if the universe is only about 13.8 billion years old? Shouldn't light have only had time to travel 13.8 billion light-years? This is where things get truly mind-bending. The universe is expanding. Space itself is stretching. When light from a distant galaxy was emitted billions of years ago, it started traveling toward us. But while that light was traveling, space was expanding, which means the distance the light had to travel kept increasing. By the time the light reaches us, the galaxy that emitted it has moved much farther away than it was when the light was emitted. In fact, the most distant galaxies we can see are now about 46.5 billion light-years away, even though the light we're seeing from them was emitted only about 13.1 billion years ago, shortly after the Big Bang. During the 13.1 billion years that light has been traveling toward us, the expansion of space has carried those galaxies much farther away. So the observable universe is about 93 billion light-years across, the distance from one edge to the other, passing through Earth in the middle, and it contains an estimated 2 trillion galaxies, each with billions or trillions of stars. The numbers become so large that they lose meaning. 2 trillion galaxies, each galaxy containing an average of perhaps 100 billion stars. That's 200 billion trillion stars in the observable universe, a number so large that there are more stars in the universe than grains of sand on all the beaches on Earth. and the distances between these objects are measured in light years, millions of light years, billions of light years. These are distances that literally break human comprehension. We can calculate them, we can measure them, we can write them down, but we cannot truly grasp what they mean. Let's think more carefully about what exists in the spaces between stars, because this empty space, measured in light years, is actually one of the most important parts of the universe. When we talk about the distance between stars being measured in light years, we're talking about vast reaches of space that are almost, but not quite, completely empty. Interstellar space, the space between stars, contains about 1 atom per cubic centimeter on average. That might not sound like much, and it's not. For comparison, the air you're breathing right now contains about 25 billion atoms per cubic centimeter. The best vacuum we can create in laboratories on Earth still contains millions of atoms per cubic centimeter. Interstellar space is emptier than anything we can create artificially. 1 atom per cubic centimeter. That's almost nothing. And yet, when you're talking about volumes measured in cubic light years, even this incredibly thin matter adds up. A cubic light year contains about 60 trillion cubic miles of space. If there's 1 atom per cubic centimeter in that space, and there are about 16.4 billion cubic centimeters in a cubic mile, that's a lot of atoms spread across that cubic light year. This interstellar medium, as astronomers call it, is mostly hydrogen, the simplest and most abundant element in the universe, with some helium and traces of heavier elements. It's not uniformly distributed. Some regions are denser, forming clouds where new stars will eventually form. Other regions are even emptier, swept clean by radiation and stellar winds from nearby stars. Between stars, you'd also find cosmic rays, high-energy particles traveling through space at nearly the speed of light. You'd find photons, particles of light from every star in the galaxy, crossing through this space on their journeys of years or centuries or millennia. You'd find magnetic fields, weak but present, threading through space and affecting the motion of charged particles. You'd find dust, tiny grains of solid matter, carbon and silicon and iron, the debris of dead stars scattered through space. This dust is important. It's where planets eventually form. It's the raw material for new solar systems. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, all of it was forged in stars that lived and died billions of years ago. Those atoms were scattered into interstellar space when those stars died, mixed with the hydrogen and helium left over from the Big Bang, and eventually incorporated into new stars and planets, including our Sun and Earth. We are, quite literally, made of stardust, atoms that have traveled light years through interstellar space between their creation in ancient stars and their incorporation into our bodies. This material cycles through the galaxy over billions of years. Stars form from collapsing clouds of gas and dust. They burn for millions or billions of years, depending on their mass. They die and return material to interstellar space. That material drifts through space for millions of years, perhaps light years from where it started. Then it collapses into new stars, and the cycle continues. Our Sun is probably a third-generation star, meaning it formed from material that had already been through 2 previous generations of stars. The atoms in your body have been part of multiple stars over the history of the galaxy. They've traveled light years through interstellar space multiple times. They've witnessed the galaxy evolve over billions of years. And now they're part of you, arranged in the complex patterns that make up a human being, able to think and feel and wonder about their own origins. Between stars, traveling through this near-empty space, you'd also find the very occasional spacecraft sent from civilizations, assuming civilizations exist besides our own. We've sent 5 spacecraft on trajectories that will eventually take them out of the solar system and into interstellar space. Pioneer 10 and Pioneer 11 launched in the 1970s, both now silent, their power sources long dead. Voyager 1 and Voyager 2 launched in 1977, still operational, still sending back data, now the most distant human-made objects in existence. And New Horizons, launched in 2006, which flew past Pluto in 2015 and is now heading into the outer solar system. These spacecraft are traveling at speeds between about 30,000 and 38,000 miles per hour. That sounds fast, and by human standards it is, but on cosmic scales it's incredibly slow. At these speeds, it would take these spacecraft tens of thousands of years to reach even the nearest stars. Voyager 1, traveling at about 38,000 miles per hour, covers about 1 billion miles every 3 years. That sounds like a lot until you realize that 1 light year is about 5.88 trillion miles. So Voyager 1 would need about 17,600 years to travel 1 light year. To reach Proxima Centauri, at 4.24 light years, would take about 74,600 years. When Voyager 1 was launched in 1977, humans had barely invented agriculture. We were just beginning to build the first cities. Writing hadn't been invented yet. By the time Voyager 1 covers the distance to Proxima Centauri, assuming it survives that long, human civilization will either have advanced beyond recognition or ceased to exist. These spacecraft carry messages, plaques, and golden records with information about Earth and humanity, on the off chance that some other civilization might find them someday. It's a beautiful gesture, but the odds of any civilization actually finding these tiny objects drifting through the vast emptiness of interstellar space are vanishingly small. Space is just so big, and these spacecraft are so small, and they're not headed toward any particular star system. They're just drifting outward, slowly, through space measured in light years, space that will take them tens of thousands of years to cross. These spacecraft represent both the achievement of reaching beyond our planet and the profound limitations imposed by the speed of light and the distances measured in light, years. We can send machines into interstellar space, but those machines will drift for millennia before reaching any destination. If there are other civilizations out there, they face the same constraints. They might be able to send messages, signals traveling at the speed of light, but those signals still take years or centuries to cross interstellar distances. A civilization 10 light years away could send us a message, and we wouldn't receive it for 10 years. If we replied immediately, they wouldn't get our response for another 10 years. Any conversation would proceed at a glacial pace, exchanges taking decades. By the time you received a response to your first message, you might have forgotten what you asked, or the society that sent the response might have changed significantly in the intervening decades. This is one of the fundamental facts of a universe measured in light years. Communication is slow, limited by the speed of light. There's no getting around it, no shortcut, no clever trick that lets you communicate faster. The speed of light is absolute, and distances are measured in light years, which means time delays are measured in years. If there's an interstellar civilization out there, a federation of worlds spanning multiple star systems, their civilization must operate on timescales of years or decades. Messages between star systems would take years to deliver and years to receive responses. Trade would be essentially impossible. You can't have a functioning economy if goods take decades or centuries to ship, and there's a years-long delay in all communications. Cultural exchange would be slow, ideas and arts spreading between stars over generations rather than instantly. Political unity would be difficult. How do you maintain a single government when the leadership on one world can't communicate with the leadership on another world except with years-long delays? An interstellar civilization if such a thing exists, would have to be fundamentally different from any civilization we can imagine, based on our experience, where communication is essentially instantaneous and travel takes hours or days at most. The light year doesn't just define distances in space, it defines the structure of any civilization that spans those distances. These are distances that literally break human comprehension. We can calculate them, we can measure them, we can write them down, but we cannot truly grasp what they mean. Let me try to give you one more way to think about this. One more attempt to make this somehow more relatable. Imagine you're in a car driving at 60 miles per hour, a reasonable highway speed. If you drove at 60 miles per hour continuously, never stopping, never slowing down, it would take you about 44 days to drive around the Earth's equator. That's a long time, but it's conceivable. To drive to the moon at 60 miles per hour would take about 165 days, about 5.5 months. To drive to the sun would take about 176 years. You'd be driving for generations. Your great-great-great-grandchildren might complete the journey. To drive to Proxima Centauri, the nearest star, at 60 miles per hour would take about 47 million years. Modern humans have only existed for about 300,000 years. The entire human genus, Homo, has only existed for about 2.8 million years. To drive to Proxima Centauri would take about 16 times longer than the entire history of the human genus. You'd have to drive continuously at 60 miles per hour for 47 million years. When you started driving, humans wouldn't exist yet. Apes would barely exist. Early primates would be just starting to evolve. By the time you reached Proxima Centauri, humans would have evolved from tree-dwelling primates, developed tools, discovered fire, built civilizations, invented agriculture, writing, mathematics, science, space travel, and probably gone extinct or evolved into something unrecognizable. And Proxima Centauri is our nearest stellar neighbor. The stars you see in the night sky are mostly much farther away. To drive to Betelgeuse at 60 miles per hour would take about 6 billion years. That's longer than Earth has existed. Earth formed about 4.54 billion years ago. If you started driving to Betelgeuse when Earth formed, you'd only be about 3/4 of the way there now. These distances are so vast that they defy comprehension. And this brings us to one of the most profound consequences of the finite speed of light and the vast distances measured in light years. When we look at the universe, we're looking into the past. Every object we see is seen not as it is now, but as it was when the light left it. The sun is seen as it was 8 minutes and 20 seconds ago. Proxima Centauri is seen as it was 4.24 years ago. Betelgeuse is seen as it was 550 years ago. The center of the Milky Way is seen as it was 26,000 years ago. Andromeda is seen as it was 2.5 million years ago. Distant galaxies billions of light years away are seen as they were billions of years ago, when the universe was young. This means that when we look deep into space, we're also looking deep into time. The Hubble Space Telescope and the James Webb Space Telescope can see galaxies so distant that the light from them has been traveling for over 13 billion years. We're seeing these galaxies as they were when the universe was less than 1 billion years old, when the first stars and galaxies were forming, when the universe looked completely different than it does today. These galaxies, as they exist now, we cannot see. The light showing us their current state hasn't reached us yet. It won't reach us for billions of years. By the time we see these galaxies, as they are today, humans will be long extinct, the sun will have died, Earth itself will be gone. This creates a strange situation where the universe we observe is a patchwork of different times. Nearby objects are seen in the relatively recent past, distant objects are seen in the ancient past, and the most distant objects are seen at a time when the universe was young and fundamentally different. We can never see the universe as it is right now in its entirety. We can only see a history, a collection of snapshots from different moments in cosmic time, all arriving at Earth simultaneously because they were emitted at different distances and have taken different amounts of time to reach us. There's another profound implication of light years that people often don't think about. The observable universe has an edge, not a physical edge, but a horizon beyond which we cannot see. This horizon exists because light has only had a finite amount of time to reach us since the Big Bang. Light from objects beyond a certain distance simply hasn't had time to reach us yet. The universe might extend far beyond what we can see, perhaps infinitely far, but we can only observe the portion within our cosmic horizon. And because the universe is expanding, this horizon is growing. Every second, light from more distant objects is reaching us for the first time. We're constantly seeing farther into the universe, seeing galaxies that were previously too distant for their light to have reached us yet. But there's a twist. The universe isn't just expanding, it's accelerating. Some mysterious force, which we call dark energy, is causing the expansion to speed up. This acceleration has a strange consequence. There are galaxies that we can see today whose light will never reach observers in the far future. As the expansion accelerates, these galaxies will recede from us faster and faster. Eventually, they'll be receding faster than the speed of light. Not because they're moving through space faster than light, which is impossible, but because space itself is expanding so fast that the distance between us and them increases faster than light can cross it. When that happens, light emitted from those galaxies will never reach us. It will be carried away by the expansion of space before it can make the journey. In the far future, trillions of years from now, the observable universe will be much emptier. Most galaxies will have been carried beyond our cosmic horizon by the accelerating expansion. Future civilizations, if they exist, will see a universe that contains only their local group of gravitationally bound galaxies. Everything else will have disappeared from view, carried away by expansion. They won't be able to see the distant galaxies we can see today. They won't have evidence that the universe is expanding. They'll think their local group is the entire universe, a small island surrounded by empty darkness. All the knowledge we've gained about cosmology, about the Big Bang, about the history and fate of the universe, will be unavailable to them unless we pass it on somehow. This is one of the strange consequences of living in an expanding universe where light speed is finite. The observable universe changes over time, not just because we build better telescopes, but because the universe itself is evolving, and some information is only available for a limited window of cosmic time. We happen to live in that window for a lot of crucial information about the cosmos. Let's talk about what all of this means for actually traveling to other stars. Science fiction often depicts starships zipping around the galaxy, visiting different star systems the way we visit different countries. But the reality of the distances involved makes this extraordinarily difficult, perhaps impossible with any technology we can currently imagine. Let's say we want to send a mission to Proxima Centauri, the nearest star. With current rocket technology, the kind we use for missions to Mars or the outer planets, the journey would take tens of thousands of years. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. It's been traveling for over 45 years and has covered about 14.5 billion miles. Sounds impressive, until you realize that's only about 0.0025 light-years. After 45 years of travel, Voyager 1 has covered about 0.06% of the distance to Proxima Centauri. At its current speed, it would take Voyager 1 about 70,000 years to reach Proxima Centauri, and that's if it were headed in that direction, which it's not. To make interstellar travel remotely practical, we'd need to go much faster. Let's say we could build a spacecraft that travels at 1% the speed of light. That's still enormously fast by current standards, about 1,860,000 miles per hour, but it's a goal that's been proposed for future missions. At 1% the speed of light, a trip to Proxima Centauri would take about 424 years. That's multiple human lifetimes, but it's within the realm of possibility. You could imagine a generation ship, a spacecraft designed to sustain a human population for centuries, with multiple generations living and dying during the journey. The people who arrive at Proxima Centauri would be the great-great-great-great-great-grandchildren of the people who launched the mission. The engineering challenges of building such a ship would be enormous. You'd need to create a completely self-sustaining ecosystem, air and water recycling, food production, waste management, all functioning perfectly for centuries, without any possibility of resupply or outside help. You'd need to maintain genetic diversity in a small population to avoid inbreeding problems over multiple generations. You'd need to maintain social stability, preventing conflicts that could destroy the mission or turn violent. You'd need to preserve knowledge and skills across generations, ensuring that the descendants who arrive still remember how to operate the ship and complete the mission. You'd need to maintain the technology for centuries, preventing degradation, replacing worn-out parts, adapting to unexpected failures. All of this in a confined space, perhaps a few city blocks worth of habitable area, with no possibility of expanding or escaping. It's a psychological challenge as much as a technological one. Could a human population remain psychologically healthy, confined to a small space for 400 years? Would they stay committed to a mission that none of them chose, that was chosen by ancestors they never knew, whose outcome they won't live to see? Would social structures and governance systems remain stable across so many generations without outside contact or influence? These are open questions, and they make generation ship seem daunting even if we solve the technological challenges. At 10% the speed of light, the trip drops to about 42.5 years, still a lifetime, but a single human lifetime. Astronauts who launched as young adults might still be alive, though elderly, when they arrived. This seems more manageable. You don't have the generational issues. The crew that launches is mostly the crew that arrives. But 10% light speed creates new problems. At these velocities, even tiny particles in space become dangerous. Space isn't perfectly empty. There's about 1 atom per cubic centimeter of interstellar space, plus occasional dust grains. At 10% light speed, collisions with these particles release enormous amounts of energy. A single hydrogen atom hitting the ship at 10% light speed would impact with the energy of a high-speed rifle bullet. A grain of dust the size of a pinhead would hit with the energy of several kilograms of TNT exploding. Any ship traveling at these speeds would need massive shielding in front, perhaps meters thick, just to survive the impacts with interstellar matter. And that shielding adds weight, which requires more energy to accelerate, which requires a bigger propulsion system, which adds more weight, creating a vicious cycle. There's also radiation. Cosmic rays and high-energy particles that permeate space would be Doppler shifted to even higher energies from the ship's perspective. The crew would need substantial radiation shielding, adding even more weight. And at 10% light speed, relativistic effects start to become noticeable. Time dilation would mean that time passes slightly slower for the crew than for people on Earth, though the effect would be small, only a few years difference over the course of the journey. At 50% the speed of light, the trip takes about 8.5 years. Now we're getting into something that seems almost manageable. You could send astronauts who would return within their working lifetime, assuming you could accelerate to 50% light speed and then decelerate again at the destination, which would require enormous amounts of energy. But even at 50% light speed, you're still limited to visiting only the very nearest stars. Betelgeuse at 50% light speed would take 1,100 years each way. The center of the galaxy would take 52,000 years. Andromeda would take 5 million years. And we don't know how to reach even 1% light speed with current technology, let alone 50%. The problem is energy. To accelerate a spacecraft to a significant fraction of light speed requires enormous amounts of energy. The faster you want to go, the more energy you need, and the amount of energy increases dramatically as you approach light speed because of relativistic effects. Let me give you some numbers to make this concrete. A spacecraft with a mass of 1,000 kilograms, about the mass of a small car, traveling at 10%, the speed of light has a kinetic energy of about 4.5 times 10 to the 18th joules. That's roughly the total energy consumption of the entire United States for 2 years. Just to accelerate one small spacecraft to 10% light speed, to reach 50% light speed would require about 115 times 10 to the 18th joules. Roughly the energy the entire world uses in 50 years. And that's just for a 1,000 kilogram spacecraft with no payload, no crew, no life support, no scientific instruments. A spacecraft capable of carrying humans and keeping them alive would need to be much larger, requiring proportionally more energy. And you'd need to accelerate that energy, whatever fuel or power source you're using, along with the ship, which compounds the problem. Various proposals have been made to solve this energy problem. Nuclear pulse propulsion, originally conceived in the 1950s under Project Orion, would work by detonating nuclear bombs behind the spacecraft and using a massive shock absorber plate to convert the explosion energy into forward motion. Studies suggested this could theoretically reach a few percent of light speed. The engineering is terrifying. You're riding a controlled sequence of nuclear explosions, but the physics works. The project was abandoned partially due to the Nuclear Test Ban Treaty, and partially because nobody wanted to launch hundreds or thousands of nuclear weapons into space. Antimatter rockets would use matter-antimatter annihilation, the most energy-dense reaction possible. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy, according to E equals mc squared. This is far more efficient than nuclear fission or fusion, which convert less than 1% of mass to energy. In principle, an antimatter rocket could reach significant fractions of light speed with reasonable amounts of fuel. The problem is producing and storing antimatter. We can create tiny amounts in particle accelerators, a few atoms at a time, at enormous cost. The total amount of antimatter ever produced by humans would barely be enough to boil a cup of water. Producing the tons of antimatter needed for a starship would require energy production capabilities far beyond anything we currently have. And storing antimatter is incredibly difficult. It must be kept from touching any normal matter, or it annihilates instantly. We'd need magnetic containment systems that could reliably contain tons of antimatter for years without any failure. A single containment failure would result in a massive explosion, possibly destroying the ship and killing everyone aboard. Laser sail propulsion, proposed by physicist Robert Forward and others, would work by pushing a lightweight spacecraft using powerful lasers from Earth or from the Sun. The spacecraft would have a large, thin, reflective sail, perhaps square miles in area, but only microns thick. Lasers would shine on the sail, and the radiation pressure from the reflected light would push the ship forward. This has the advantage that you don't need to carry fuel. The energy comes from the lasers back home. The Breakthrough Starshot project, announced in 2016, proposes using this method to send tiny spacecraft, each about the size of a postage stamp weighing less than a gram, to Alpha Centauri. Arrays of powerful ground-based lasers would accelerate these tiny craft to about 20% light speed in a matter of minutes. The journey to Alpha Centauri would take about 20 years, and images from the Alpha Centauri system would arrive back at Earth about 24 years after launch. It's an ambitious project facing enormous technical challenges. The lasers would need to be extraordinarily powerful, perhaps 100 gigawatts or more, focused with incredible precision to hit a tiny moving target, accelerating away from Earth at tremendous speed. The spacecraft would need to survive the intense laser heating during acceleration without melting or vaporizing. They'd need to survive the journey through interstellar space without any repairs or maintenance. They'd need to automatically conduct observations and transmit data back across interstellar distances using their own tiny power sources. But if successful, it would represent the first human-made object to reach another star system within a human lifetime. It wouldn't carry humans, but it would carry our instruments, our observations, our curiosity. Fusion ramjets, originally conceived by physicist Robert Bussard in the 1960s, would collect interstellar hydrogen using huge magnetic scoops, perhaps thousands of miles across. The collected hydrogen would be funneled into a fusion reactor, where it would be fused into helium, releasing energy that propels the ship forward. In principle, this would give the ship unlimited range. It would never run out of fuel because it's collecting fuel as it goes. Theoretical calculations suggested it might reach 10 to 20% of light speed. The problems are numerous. First, we haven't yet achieved controlled fusion in reactors on Earth, despite decades of effort and billions of dollars spent. Doing it in a spacecraft while traveling through space adds enormous additional complexity. Second, the magnetic scoop would need to be gigantic, possibly thousands of miles across, to collect enough hydrogen from the incredibly thin interstellar medium. Building and maintaining such a structure while traveling at relativistic speeds through space, full of dust and radiation, would be extraordinarily difficult. Third, at high speeds, the collected hydrogen would be Doppler shifted to high energies, effectively becoming deadly radiation that would need to be handled carefully. And fourth, the drag from scooping up all that hydrogen might actually slow the ship down more than the fusion propulsion speeds it up, making the whole concept self-defeating. These are just proposals, none of them proven, none of them close to actual implementation. Some might be possible with technologies we can imagine developing in the next century or two. Some might turn out to be impossible for fundamental physical reasons we don't yet understand. But all of them share a common limitation. They're bound by the speed of light. Even the most optimistic proposals, even antimatter rockets or laser sails or fusion ramjets, can't exceed the speed of light. They might reach 10%, 20%, maybe 50% light speed, with enough engineering and resources, but not faster than light. And that means journeys measured in decades or centuries, even to the nearest stars, measured in thousands or millions of years to distant parts of the galaxy. Let's talk about what all of this means for actually traveling to other stars. Science fiction often depicts starships zipping around the galaxy, visiting different star systems the way we visit different countries. But the reality of the distances involved makes this extraordinarily difficult, perhaps impossible with any technology we can currently imagine. Let's say we want to send a mission to Proxima Centauri, the nearest star. With current rocket technology, the kind we use for missions to Mars or the outer planets, the journey would take tens of thousands of years. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. It's been traveling for over 45 years and has covered about 14.5 billion miles. Sounds impressive, until you realize that's only about 0.0025 light-years. After 45 years of travel, Voyager 1 has covered about 0.06% of the distance to Proxima Centauri. At its current speed, it would take Voyager 1 about 70,000 years to reach Proxima Centauri, and that's if it were headed in that direction, which it's not. To make interstellar travel remotely practical, we'd need to go much faster. Let's say we could build a spacecraft that travels at 1% the speed of light. That's still enormously fast by current standards, about 1,860,000 miles per hour, but it's a goal that's been proposed for future missions. At 1% the speed of light, a trip to Proxima Centauri would take about 424 years. That's multiple human lifetimes, but it's within the realm of possibility. You could imagine a generation ship, a spacecraft designed to sustain a human population for centuries, with multiple generations living and dying during the journey. The people who arrive at Proxima Centauri would be the great-great-great-great-great-grandchildren of the people who launched the mission. At 10% the speed of light, the trip drops to about 42.5 years. Still a lifetime, but a single human lifetime. Astronauts who launched as young adults might still be alive, though elderly, when they arrived. At 50% the speed of light, the trip takes about 8.5 years. Now we're getting into something that seems almost manageable. You could send astronauts who would return within their working lifetime, assuming you could accelerate to 50% light speed and then decelerate again at the destination, which would require enormous amounts of energy. But even at 50% light speed, you're still limited to visiting only the very nearest stars. Betelgeuse at 50% light speed would take 1,100 years each way. The center of the galaxy would take 52,000 years. Andromeda would take 5 million years. And we don't know how to reach even 1% light speed with current technology, let alone 50%. The problem is energy. To accelerate a spacecraft to a significant fraction of light speed requires enormous amounts of energy. The faster you want to go, the more energy you need, and the amount of energy increases dramatically as you approach light speed because of relativistic effects. Various proposals have been made. Nuclear pulse propulsion, where you detonate nuclear bombs behind the spacecraft to push it forward. Antimatter rockets, where you annihilate matter and antimatter to produce energy. Laser sails, where you push a lightweight spacecraft using powerful lasers from Earth or from the Sun. Fusion ramjets, where you collect interstellar hydrogen as you travel and use it as fuel for fusion reactions. All of these are theoretically possible, but all of them require technologies far beyond what we currently have. And even if we solved the propulsion problem, there are other challenges. At high speeds, even tiny particles become dangerous. A grain of dust hitting a spacecraft traveling at 10% light speed would release energy equivalent to a grenade exploding. Interstellar space isn't perfectly empty. There's about 1 hydrogen atom per cubic centimeter, and at high speeds, those atoms become deadly radiation. You'd need massive shielding, which adds weight, which requires more energy to accelerate. Communication is another problem. Even if you manage to send a spacecraft to another star system, staying in contact would be difficult. Radio signals take years to travel between stars. A message from a probe orbiting Proxima Centauri would take 4.24 years to reach Earth. If something went wrong, if the spacecraft needed instructions, there would be a 4.24-year delay before Earth even knew there was a problem, and another 4.24-year delay before new instructions reached the spacecraft. By the time the spacecraft received those instructions, the situation would have changed. The problem might have gotten worse, or resolved itself, or destroyed the spacecraft. Interstellar missions would need to be highly autonomous, capable of making decisions and solving problems on their own without waiting for instructions from Earth. And then there's the question of why. Why spend enormous resources to send a spacecraft on a journey that will take decades or centuries when we can learn so much by observing from Earth using telescopes? The James Webb Space Telescope, launched in 2021, can observe galaxies billions of light-years away. It cost about $10 billion to build and launch. An interstellar mission to even the nearest star would cost far more and would take far longer to return results. From a purely scientific standpoint, telescopes give us much better return on investment for understanding the universe. But there's something uniquely compelling about actually going there, about sending a probe to another star system, seeing it up close, maybe even sending humans eventually. It represents something beyond science, a statement about humanity's place in the cosmos, a drive to explore and expand beyond our home planet. Whether that's worth the cost is a question that goes beyond science and engineering into philosophy and values. Some scientists and engineers are working on it anyway. The Breakthrough Starshot project, announced in 2016, aims to send tiny spacecraft, each about the size of a postage stamp, to Alpha Centauri at about 20% the speed of light. The spacecraft would be accelerated using powerful lasers on Earth, pushing lightweight solar sails. If successful, the journey would take about 20 years, and images from Alpha Centauri would arrive back at Earth about 24 years after launch. It's an ambitious project, facing enormous technical challenges, but it represents a serious attempt to make interstellar travel actually happen within a human lifetime. There's also the question of what we might find when we get to another star. Proxima Centauri has at least 2 known planets, one of which, Proxima Centauri b, orbits in the star's habitable zone, the region where liquid water could exist on a planet's surface. Does Proxima Centauri b have life? We don't know. It's only 4.24 light-years away, but that distance is so vast that we can't currently see the planet in enough detail to tell if it has an atmosphere, oceans, continents, or life. Sending a probe there would answer those questions, but it would take decades or centuries depending on the speed we could achieve. And what if we found life? What if Proxima Centauri b has a biosphere, ecosystems, perhaps even intelligent life? The discovery would be monumental, the most important discovery in human history, but the distance would still be 4.24 light-years. We couldn't have a conversation with them. A message would take 4.24 years to reach them, and another 4.24 years for a response to come back. Any interaction would happen in slow motion, messages exchanged over years or decades. You could imagine sending a question and receiving a response years later, perhaps answered by someone different than the person who received your question, or in a different context, because their society had changed in the intervening years. It would be unlike any communication humans have ever experienced, shaped entirely by the finite speed of light and the vast distances measured in light-years. This brings us back to the fundamental truth about light-years. They're not just a measurement, they're a barrier, a constraint on what's possible. The universe is organized on scales measured in light-years, billions of light-years, and we're confined to a tiny planet orbiting one star. Our entire species, everything we've ever accomplished, has happened on a speck of dust in a cosmos measured in light-years. We can observe the universe, we can study it, we can understand it using mathematics and physics and telescopes, but physically traveling through it, visiting other stars and galaxies, that's something that may be forever beyond our reach. Not because we lack imagination or determination, but because the distances are so vast and the speed of light is so limiting. There's a profound isolation built into the structure of the cosmos. Stars are separated by light-years, galaxies by millions of light-years, galaxy clusters by hundreds of millions of light-years. If there are other civilizations out there, and statistically there probably are, they face the same isolation. They're confined to their home planets or solar systems, able to observe the universe but unable to physically reach more than a tiny fraction of it. Some scientists speculate about wormholes or warp drives, theoretical shortcuts through space-time that might allow faster-than-light travel without actually moving faster than light. These ideas come from general relativity, Einstein's theory of gravity, which describes space-time as a flexible fabric that can be bent and curved. In principle, you might be able to create a shortcut through space-time, a tunnel connecting two distant points, allowing you to travel between them without covering the intervening distance. Or you might warp space-time around your spacecraft, contracting space in front and expanding space behind, allowing you to surf through space faster than light without violating relativity. These ideas are mathematically consistent with general relativity, but they require exotic forms of matter and energy that might not exist. Negative energy density, for example, which would be needed to hold a wormhole open or to create a warp drive bubble. We've never observed negative energy density in nature, and we don't know how to create it. Most physicists think it's probably impossible. Even if it exists, the amounts required would be enormous, perhaps requiring more energy than exists in the observable universe. So while faster-than-light travel is fun to think about and makes for great science fiction, it's almost certainly impossible in reality. We're stuck with light speed as an absolute limit, and that means we're stuck with a universe measured in light years that we can observe but not easily explore. Let me explain wormholes in more detail, because they're such a fascinating idea even if they're probably impossible. In general relativity, space-time is described as a four-dimensional surface that can be curved and warped by mass and energy. When we draw pictures of this, we usually simplify to two dimensions, showing space-time as a rubber sheet that gets bent and warped by heavy objects. Now imagine taking this sheet and bending it so that two distant points come close together, then connecting those points with a tunnel through the sheet. That's a wormhole, a shortcut through space-time. You'd enter one end, which might be here in our solar system, travel through the tunnel for what feels like a short distance, maybe just a few miles or even less, and emerge at the other end, which might be many light years away. From your perspective, you've only traveled a short distance, but from the perspective of someone watching in normal space, you've effectively jumped across light years instantaneously, or nearly so. You haven't traveled faster than light in any local sense, you've just taken a shortcut through a different part of space-time. The mathematics of general relativity does allow solutions that include wormholes. They're not forbidden by the equations. But the question is whether they can actually exist in nature. The first problem is stability. Simple wormholes, according to the equations, would collapse immediately. The tunnel would pinch closed before anything could pass through. To hold a wormhole open, you'd need something pushing outward on the walls of the tunnel, counteracting the tendency to collapse. That something would need to have negative energy density, pushing outward, rather than pulling inward like normal matter does. This is sometimes called exotic matter, and we don't know if it exists. There's something called the Casimir effect in quantum physics, where two metal plates placed very close together experience a tiny attractive force that can be interpreted as arising from negative energy density in the space between them. Some physicists have speculated this might be used to stabilize a wormhole, but the amounts of negative energy produced in the Casimir effect are infinitesimally small. To hold open a wormhole big enough for a spacecraft to pass through would require enormous amounts of negative energy, far more than we could conceivably produce. Some calculations suggest you'd need negative energy equivalent to the mass of Jupiter or even a star. We have no idea how to create or manipulate such enormous amounts of exotic matter, assuming it's even possible. There's also the question of whether wormholes could be created in the first place. Even if you could stabilize one with exotic matter, how do you make one? There are no natural processes we know of that would create wormholes. You'd have to manufacture one somehow, manipulating space-time on enormous scales, and we don't know how to do that. It might require technology so advanced as to be indistinguishable from magic, to use Arthur C. Clarke's phrase. And there's a deeper problem: causality. If wormholes allowed faster-than-light travel, they might also allow time travel, which creates paradoxes. If you could travel through a wormhole to a distant location faster than light could travel there, then in some reference frames, you'd be arriving before you left, traveling backwards in time. This could allow you to go back and prevent your own departure, creating a logical contradiction. Most physicists suspect that the laws of physics somehow prevent this, that any configuration of matter and energy that would allow time travel paradoxes is forbidden by some deeper principle we don't yet understand. Stephen Hawking called this the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel and the paradoxes it would create. If he's right, then wormholes that could be used for faster-than-light travel probably can't exist. Warp drives are another idea that comes from general relativity. The concept was developed mathematically by physicist Miguel Alcubierre in 1994. The idea is that you create a bubble of space-time around your spacecraft. Inside the bubble, you're stationary relative to the space-time immediately around you. But you manipulate space-time outside the bubble, contracting space in front of you and expanding space behind you. This creates a wave of distorted space-time that carries you forward. From your perspective inside the bubble, you're not moving. The space around you is moving, carrying you along. From the perspective of someone outside, you appear to be traveling faster than light. But you're not actually violating relativity, because you're not moving through space. Space itself is moving. It's a clever idea, and the mathematics works within general relativity, but again, it requires exotic matter with negative energy density. Alcubierre's original calculation suggested you'd need negative energy equivalent to the mass of Jupiter to create a warp bubble big enough for a small spacecraft. Later refinements brought this down, but it's still an enormous amount of exotic matter that we don't know how to create. There are also practical problems. How do you control the warp bubble from inside when you're causally disconnected from the edges of the bubble? Information can't travel faster than light, so you can't send control signals to the front of the bubble to tell it where to go. The bubble, once created, might be uncontrollable, carrying you in whatever direction it was initially aimed with no ability to steer or stop. And if you could somehow stop it, the accumulated energy in the distorted space-time might be released catastrophically, possibly destroying anything in front of the ship. These are serious problems that might make warp drives fundamentally impractical, even if we solved the exotic matter problem. Again, most physicists think warp drives are probably impossible for reasons we don't yet fully understand. The universe seems to enforce the light speed limit very strictly, and any attempt to bypass it seems to run into fundamental obstacles. So we're back to slower than light, travel through distances measured in light years, with all the limitations that implies. Some scientists speculate about wormholes or warp drives, theoretical shortcuts through space-time that might allow faster-than-light travel without actually moving faster than light. These ideas come from general relativity, Einstein's theory of gravity, which describes space-time as a flexible fabric that can be bent and curved. In principle, you might be able to create a shortcut through space-time, a tunnel connecting two distant points, allowing you to travel between them without covering the intervening distance. Or you might warp space-time around your spacecraft, contracting space in front and expanding space behind, allowing you to surf through space faster than light without violating relativity. These ideas are mathematically consistent with general relativity, but they require exotic forms of matter and energy that might not exist. Negative energy density, for example, which would be needed to hold a wormhole open or to create a warp drive bubble. We've never observed negative energy density in nature, and we don't know how to create it. Most physicists think it's probably impossible. Even if it exists, the amounts required would be enormous, perhaps requiring more energy than exists in the observable universe. So while faster-than-light travel is fun to think about, and makes for great science fiction, it's almost certainly impossible in reality. We're stuck with light speed as an absolute limit, and that means we're stuck with a universe measured in light years that we can observe but not easily explore. Let's zoom out one more time and think about what the concept of a light year tells us about the universe and our place in it. A light year is 5.88 trillion miles. It's the distance light, the fastest thing in the universe, travels in 1 year. This distance is so vast that human brains cannot truly comprehend it. We can calculate it, measure it, use it in equations, but we cannot visualize it or grasp it intuitively. Our brains didn't evolve to understand distances this large. Nearby stars are several light years away. Our galaxy is 100,000 light years across. Nearby galaxies are millions of light years away. The observable universe is 93 billion light years across. These distances are real. They can be measured. They can be verified through multiple independent methods, but they exist on scales that are completely alien to human experience. And yet we can understand them, at least intellectually. We can work with them using mathematics. We can incorporate them into physical theories. We can make predictions about the universe based on them, and test those predictions with observations. This is one of the remarkable things about human intelligence. We can understand things that we cannot directly experience. We can comprehend distances far larger than we'll ever travel, timescales far longer than we'll ever live, objects far smaller than we can see. Our minds can reach beyond the limitations of our bodies and our immediate sensory experience. The light year represents both the vastness of the cosmos and the power of human understanding. It's a distance that breaks our brains, that challenges the very limits of human comprehension, but it's also a tool that allows us to measure and explore the universe, to understand our place in the cosmic order. When you look up at the night sky and see stars, you're seeing light that has traveled for years or centuries or millennia across the vast empty spaces between stars. You're looking deep into the past, seeing the universe not as it is now, but as it was when that light began its journey. Every star is a sun, perhaps with planets, perhaps with life. And every star is separated from every other star by distances measured in light years, vast gulfs of space that light takes years to cross. The universe is unimaginably large. It contains 2 trillion galaxies, each with billions or trillions of stars. It spans 93 billion light years from edge to edge, at least the portion we can observe. And somewhere in this vast cosmos, on a small rocky planet orbiting an ordinary star in an unremarkable galaxy, a species evolved that could look up at the stars and figure out how far away they are, that could measure distances in light years, that could understand, at least in principle, the true scale of the universe. We are tiny, insignificant on cosmic scales. Earth is a pale blue dot, barely visible from even the edge of our own solar system. Our entire civilization, all of human history, every person who has ever lived, everything we've accomplished, all of it has happened on this tiny speck orbiting one star among hundreds of billions in a galaxy that's one among trillions. We are tiny, insignificant on cosmic scales. Earth is a pale blue dot, barely visible from even the edge of our own solar system. Our entire civilization, all of human history, every person who has ever lived, everything we've accomplished, all of it has happened on this tiny speck orbiting one star among hundreds of billions in a galaxy that's one among trillions. And yet, we can understand this. We can comprehend, at least intellectually, how small we are. We can measure the cosmos using units like the light year. We can look out into the universe and see it as it really is, vast beyond imagining, ancient beyond belief, filled with wonders we're only beginning to discover. Think about what this means for human existence. for our sense of meaning and purpose in the universe. For most of human history, people believed Earth was the center of everything. The sun, moon, stars, and planets all revolved around us. We were special, privileged, at the center of creation. This view was comforting. It made humans important. It gave us a central role in the cosmic drama. Then Copernicus showed that Earth orbits the sun, not the other way around. We weren't at the center, we were just another planet. Then we discovered that the sun is just one star among billions in our galaxy. We weren't even at the center of our own galaxy. We were out in a quiet spiral arm, nowhere special. Then we discovered that our galaxy is just one of billions in the universe. Our entire galaxy, with its hundreds of billions of stars, is just one small island in a cosmos containing trillions of galaxies. And we discovered that the universe is expanding, which means galaxies are moving apart, which means there is no center. Or rather, every point is equally a center. The universe looks the same from any galaxy's perspective. Earth isn't at the center because there is no center. We're not special, we're not privileged, we're not at the heart of creation. We're on a small planet, orbiting an ordinary star in an ordinary galaxy, floating in an unimaginably vast universe. Distances are measured in light years, billions of light years, and we can barely travel beyond our own planet. This is sometimes called the Copernican principle, the idea that we're not special, that there's nothing privileged about our location or our time in cosmic history. It's a humbling realization, and for some people it's a disturbing one. If we're not special, if we're just an accident of chemistry on one planet among trillions of planets, what's the point? Why does anything we do matter if we're so cosmically insignificant? But there's another way to look at it, a way that's not depressing but actually inspiring. Yes, we're small, unimaginably small compared to the cosmos. Yes, we're insignificant in terms of our size and location, but we're not insignificant in terms of what we've accomplished. We're a species that evolved intelligence, that developed language, that created science and mathematics, and art and literature. We're a species that figured out how to leave our planet, if only briefly, and how to send machines to other planets and beyond. We're a species that looked up at the stars and figured out what they are, how far away they are, how they form and evolve and die. We're a species that measured distances in light years. We took a concept, the distance light travels in 1 year, and used it to map the entire observable universe. We determined that the universe is 93 billion light-years across, that it contains 2 trillion galaxies, that it's 13.8 billion years old. We traced cosmic history back to the Big Bang, forward to the eventual heat death of the universe in the far future. We figured out that we're made of stardust, that every atom in our bodies was forged in stars billions of years ago. We connected our own existence to the life cycle of stars and galaxies. We found our place in the cosmic story. That's not insignificant, that's remarkable. We're the part of the universe that became conscious, that developed the ability to understand itself. We're how the universe knows itself, experiences itself, contemplates its own existence. Carl Sagan put it beautifully. He said, "We are a way for the cosmos to know itself." The atoms that make up your body were part of stars. Billions of years ago, they drifted through interstellar space. They became part of the gas cloud that collapsed to form our solar system. They were incorporated into Earth, and eventually into living things, and eventually into you. Those atoms are now arranged in patterns complex enough to think, to wonder, to ask questions about their own origins. That's extraordinary, and the fact that it happened on a small planet in an ordinary solar system doesn't make it less extraordinary. There might be other civilizations out there, probably are, statistically speaking, but we don't know that for sure. As far as we know right now, we might be the only conscious observers in the entire universe. We might be the only beings capable of understanding that the universe exists, that it's vast beyond comprehension, that distances are measured in light years. That would make us incredibly special, not because of where we are or how big we are, but because of what we can do. And even if there are other civilizations out there, even if intelligence and consciousness are common in the universe, we're still special in our own way. We're the ones who measured the cosmos from this particular vantage point, from Earth, using these particular methods, developing this particular scientific tradition. Our understanding of the universe, expressed through units like the light year, is a unique human achievement. It's something to be proud of, something that gives meaning to human existence, even in a universe measured in light years. There's also something profound about the fact that we can understand things we can never physically reach. We can measure distances to galaxies billions of light years away, knowing that we will never visit them, that no human will ever visit them, that probably no living thing from Earth will ever reach them. The distances are too vast, the timescales too long, the speed of light too limiting. And yet we can study these distant galaxies. We can learn about their properties, their ages, their compositions. We can watch them collide and merge through telescopes, seeing events that happened billions of years ago. We can trace their histories back to the early universe, forward to their eventual fates. We can understand them, even though we'll never touch them, never visit them, never interact with them in any physical way. This is the power of science and mathematics, the ability to reach across cosmic distances with nothing but our minds and our instruments. We're physically confined to one tiny planet, but our understanding extends across the entire observable universe. That's something no other species on Earth has ever done. Other animals are confined to their immediate environments. They understand what they can directly sense and experience. Humans transcend that limitation. We understand things we've never experienced, things we never could experience. We understand black holes even though we've never been near one and would be destroyed if we were. We understand the Big Bang, even though it happened 13.8 billion years ago. We understand distant galaxies billions of light years away that we'll never visit. This ability to transcend our immediate experience, to understand the universe on its own terms rather than just in relation to our survival needs, this is one of the most distinctively human capabilities. And it's made possible by concepts like the light year, units of measurement that allow us to quantify and work with distances that completely exceed human scale. There's also a deep connection between the concept of a light year and the nature of time itself. When we say something is 10 light years away, we're saying that the light we see from it left 10 years ago. Distance and time are intrinsically connected. You can't separate them. This connection becomes even more profound when you understand Einstein's theory of relativity. Space and time aren't separate things. They're unified into a single four-dimensional structure called space-time. Events in the universe don't just have locations in space, they have locations in space-time. They occupy specific points in both space and time. The light year embodies this connection. It's explicitly a measure of distance defined in terms of time. How far does light travel in 1 year? That's a question that combines space and time into a single concept, and because nothing can travel faster than light, the light year also represents a fundamental barrier. Events separated by 1 light year in space are also separated by at least 1 year in time for any causal connection. If something happens on a planet 10 light years away, we won't know about it for 10 years. If we respond immediately, they won't know we responded for another 10 years. The connection can never be faster than the light travel time. This creates what physicists call light cones, structures in space-time that determine what events can causally affect what other events. The past light cone of an event includes everything in space-time that could have affected that event. everything whose light or influence could have reached it. The future light cone includes everything that event could potentially affect. Events outside the light cones are causally disconnected. They can't affect each other. There's no way for information or influence to pass between them. For events separated by distances measured in light years, the light cones are wide. The causal connections are slow. This is just the nature of a universe where space and time are unified and the speed of light is finite. We live in a universe where causality is limited by light speed, where actions have consequences that spread outward at the speed of light, but no faster, where distant events are not just spatially separated, but temporally separated. The light year reminds us of this fundamental structure of space-time. When we measure cosmic distances in light years, we're not just measuring space, we're measuring the structure of causality itself, the framework that determines what can affect what and how fast influences can spread. There's something both limiting and liberating about this. Limiting because it means we're causally isolated from most of the universe. Events happening right now in distant galaxies will remain unknown to us for billions of years, and by the time we learn about them, they'll be ancient history. But liberating because it means we have time, cosmic time, to develop and grow and expand before we might encounter other civilizations or face cosmic-scale threats. The speed of light limit, expressed through the light year, gives us breathing room in a vast cosmos, and yet we can understand this. We can comprehend, at least intellectually, how small we are. We can measure the cosmos using units like the light year. We can look out into the universe and see it as it really is, vast beyond imagining, ancient beyond belief, filled with wonders we're only beginning to discover. The light year is more than just a unit of measurement. It's a reminder of both how much we don't know and how far we've come. It's a distance that challenges the limits of human understanding, that shows us the universe operates on scales we never evolved to comprehend. But it's also a tool that allows us to explore that universe, to push the boundaries of human knowledge, to see farther and understand more deeply than any generation before us. That's what makes the light year so profound. It's not just a number, not just a calculation. It's a window into the true nature of reality, a measure of the cosmos that simultaneously humbles us and empowers us. And understanding it, truly understanding what a light year means, changes how you see everything. The next time you look up at the stars, remember that the light you're seeing has traveled for years or centuries across vast, empty spaces to reach your eyes. Remember that every point of light is a sun, perhaps with worlds, perhaps with life. Remember that the distances between them are measured in units that break the human mind, that challenge everything we thought we understood about space and time. And remember that despite all of this, despite the vast distances and the isolation and the limitations imposed by the speed of light, we can still reach out with our minds and our telescopes and our mathematics and understand it all. That's the power of human curiosity and intelligence. That's what it means to be a conscious being in a vast cosmos. And that's why the light year, this distance that breaks our brains, is so fundamentally important to understanding who we are and where we are in the universe. But let's think for a moment about the future, about what might be possible even given these constraints. Even if we can't travel faster than light, even if interstellar travel takes decades or centuries, humanity might still spread beyond Earth. We might establish permanent settlements on Mars, on the moons of Jupiter and Saturn, in habitats floating in space or on asteroids. We might develop technologies that make life sustainable away from Earth, technologies that let us create Earth-like environments wherever we go. Over centuries, we might slowly expand outward, generation by generation, star system by star system. Each journey taking decades or centuries, but each one establishing a new foothold, a new human community adapted to its local environment. Given enough time, thousands or millions of years, humanity or its descendants might spread throughout the galaxy, even at slower than light speeds. It would be a slow expansion, nothing like the rapid star hopping of science fiction, but it would be an expansion nonetheless. Each new settlement would be largely independent, years of light travel time away from any other settlement, unable to maintain real-time communication or any kind of unified government or culture. But they'd all trace their origin back to Earth. They'd all be part of the great diaspora of terrestrial life spreading through the galaxy. And each settlement would bring with it the knowledge and culture of Earth, adapted and modified for local conditions, but still recognizably human or descended from humans. We might also find other forms of life out there, microbial life on Mars or Europa or Enceladus, complex multicellular life on exoplanets around other stars. Finding any form of life, even simple bacteria, would be one of the most important discoveries in human history. It would tell us that life is not unique to Earth, that the chemical processes that led to life here can occur elsewhere. It would suggest that the universe might be full of life, even if most of it is simple and most planets are lifeless. And if we found intelligent life, civilizations capable of technology and science like our own, that would be even more profound. We'd know for certain that we're not alone, that consciousness and intelligence can arise independently in different environments. We might be able to communicate with them, slowly, across the light years that separate us, exchanging information and ideas, even if we could never meet in person. Or we might find the ruins of dead civilizations, evidence that intelligence arose but then failed, destroyed by war, or environmental collapse, or some other catastrophe. That would be a sobering discovery, a warning that civilization is fragile, that there's no guarantee of survival or progress. These are the questions that light years and the distances they represent make relevant. If other civilizations exist, they're separated from us by light years, by time delays in any communication, by vast gulfs of space that make physical contact difficult or impossible. The structure of the universe, measured in light years, determines how we might interact with any other intelligence out there. There's one more thing to consider: the very long-term future, billions of years from now. The universe is expanding, and that expansion is accelerating due to dark energy, a mysterious force we don't understand. In the far future, this acceleration will carry most galaxies beyond our cosmic horizon. They'll recede from us faster than light, not because they're moving through space faster than light, but because space itself is expanding faster than light can cross it. When that happens, light from those galaxies will never reach us. Trillions of years from now, the night sky will be much emptier, most galaxies will have disappeared from view, carried beyond our observable horizon by the expansion of space. Future civilizations, if they exist, will see a much lonelier universe. They'll see only their local group of gravitationally bound galaxies. Everything else will have vanished. They won't be able to see the cosmic microwave background, the afterglow of the Big Bang, because it will have been redshifted to undetectable wavelengths. They won't have evidence that the universe had a beginning or that it's expanding. They might think their local group is the entire universe, an island surrounded by infinite darkness. All the cosmological knowledge we've gained, all the understanding of the Big Bang and cosmic evolution and the large-scale structure of the universe, will be unavailable to them unless we somehow pass it on. This is a strange consequence of living in an expanding universe where light speed is finite. The observable universe changes over time, shrinking in some sense as expansion carries distant objects beyond our horizon. We happen to live at a time when the universe is still young enough and close enough that we can observe distant galaxies, measure cosmic expansion, trace history back to the Big Bang. Future civilizations won't have that luxury. They'll see a smaller, emptier universe unless they inherit our knowledge. It makes you realize that our moment in cosmic history is special not because of where we are, but because of when we are. We exist at a time when the universe is still observable, when distances measured in light years are still within our cosmic horizon. That's a privilege that won't last forever, and it makes the astronomical knowledge we're gathering now even more precious. The light year is not just a unit of measurement, it's a window into the structure of reality itself. It tells us about the relationship between space and time, about the limits of causality, about the barriers to communication and travel that are built into the fabric of the cosmos. It reminds us that we live in a vast universe, measured on scales we can barely comprehend, separated by distances that challenge the very limits of human understanding. But it also reminds us of what we've accomplished, that despite being confined to one small planet, we've measured the entire observable universe. We've figured out how far away the stars are. We've mapped the structure of galaxies. We've traced cosmic history back to its beginning. We've done all of this using nothing but our minds, our mathematics, our instruments, and our determination to understand. That's something to be proud of, something that gives meaning to human existence in a cosmos measured in light years. The next time you look up at the stars, remember that the light you're seeing has traveled for years or centuries across vast empty spaces to reach your eyes. Remember that every point of light is a sun, perhaps with worlds, perhaps with life. Remember that the distances between them are measured in units that break the human mind, that challenge everything we thought we understood about space and time. And remember that despite all of this, despite the vast distances and the isolation and the limitations imposed by the speed of light, we can still reach out with our minds and our telescopes and our mathematics and understand it all. That's the power of human curiosity and intelligence. That's what it means to be a conscious being in a vast cosmos. And that's why the light year, this distance that breaks our brains, is so fundamentally important to understanding who we are and where we are in the universe. Thanks for staying with me through this long journey across cosmic distances. The light year isn't just a measurement, it's a testament to both the vastness of the universe and the power of human understanding. And now that you truly understand what it means, you'll never look at the night sky the same way again.